Hello there, Mr. Sutton here with the AB Calculus 6-7 Extra Practice number 6 solutions on total distance. For this calculator-based free response question, we have Diego running back and forth on a straight track along the interval from 0 to 30 seconds, and Diego's velocity in feet per second is given by this v function. Great. First task, we want to know the first time, which they're forcing us to call t1, that Diego changes directions. And then we want his average velocity over the interval from 0 to t1. All right, so we're basically asking when's the first time that v of t changes sign? Well, let's look that up on our calculator. So here I am in my y equals. In y1, I've entered Diego's velocity function, this crazy thing here. And I need to graph this now. I'm going to graph it on the window from 0 to 30 for my x min and my x max. Let me go to window and enter all that. So I've already got 0 for x min. For x max, let's change that to 30. And I'll do zoom 0, zoom fit. And here's Diego, or at least here's Diego's velocity. So we just want to know the first place that this is changing sign, which is this spot right here. So let me do second trace, option 2 for 0. And then we'll just move a little bit to the left of that intersect, press enter. A little bit to the right, press enter. Enter one more time, and it comes out to about 15.3, I guess 50, if I round it off to 3 decimals. So we're going to call that spot right there T1, 15.350 seconds. And I'm actually going to store that in my calculator as well because I know I'm going to need it. So let me quit out of there, and let me press the store button. And I don't have a T1 button here. I'm just going to store this as alpha A, because why not? All right, now I can call that back whenever I want. So to find the average velocity over the interval from 0 to t1, I'm going to need an average value kind of setup. So 1 over the interval length, 1 over t1 minus 0, times the integral from 0 to t1 of, and now average velocity, we just, whatever we're averaging, we put inside the integral here. So I'm just going to put v of t dt in there. And now I'm actually going to run those numbers on my calculator. So back on the calculator, let me do, let's see, alpha y equals to get my fancy fraction form. We got 1 over, and I'm just going to do t1, which I stored as a. So alpha a. And then I need to multiply that by the integral. So math 9. And we're going from 0 to alpha a, or t1. And that's going to be velocity, so let me do alpha trace and just pull y1 up from that menu. And then let me go over here and put an x in the differential, press enter, and all of that comes out to 10.504, and that's going to be average velocity, so that's going to be in feet per second. For this part, we want to know at time 30, how far is Diego from his position at time 0. So we're just asking for Diego's displacement, which is going to just be the integral of his velocity from 0 to 30. So let's just plug that in the calculator. So there we are. Recall that I stored velocity as y1 in my y equals. So just press enter there. And that's going to be, drum roll, 128.323. And that's going to be in feet. For this part, we want the total distance Diego runs in 30 seconds. So from time 0 to time 30. This is kind of similar to part B, only now we're going to take the integral from 0 to 30 of the absolute value of Diego's velocity. So let's just run those numbers. So just like when I'm doing displacement, I've got my integral from 0 to 30. But now I'm going to do alpha window and pull up the absolute value from that menu. And I'll put alpha trace y1 in there, and now I'll do dx, press enter, and this will give us the total distance that Diego travels. This is going to take a little bit longer than the displacement because there's a lot of back and forth that the calculator has to run. We'll just let it run that off camera. So after waiting a while off camera, we eventually come up with this answer, 243.425 feet. For this last problem part, we're letting a of t represent Diego's acceleration on the interval from 0 to 30. So first part of this, using correct units, explain the meaning of the integral from 5 to 10 of a of t dt in the context of the problem. So acceleration, remember, that's the rate of change of velocity. So if I'm integrating the rate of change of velocity, I'm getting the total change of velocity over a certain time period. So this is going to be the change in velocity, which is going to be, since it's in velocity units, it's going to be in feet per second over the time interval from 5 to 10 seconds. So we need the units, we need the time units, and the time itself mentioned in there, and the fact that this is change in velocity. Now to actually find this, we don't actually know the formula for a of t. We could find it by taking the derivative of this up here, but there's actually an easier way to do this. Since a of t is really just v prime, and I'm just going to rewrite it like this, I can just use my fundamental theorem. I mean, what is the antiderivative of v prime? It's just v. So this is really just going to be v of 10 minus v of 5 if I just evaluate v of t from 5 to 10. And I can totally do that on the calculator. So here's what that looks like on the calculator. I just did alpha trace and pulled up y1 where I stored my v function, getting a lot of mileage out of that. And then press enter. That's going to be 6.765. And again, that's feet per second for those units. For this calculator-based free response problem, we have the velocity of a particle p, which is moving along the x-axis, given by Vp, where Vp of t is measured in meters per hour and t is in hours, and we've got some selected values of Vp of t up here in the table. And then they're telling us particle p is at the origin at time 0. That's good to know. So first part of this problem, we want to justify where there has to be at least one time between 0.3 and 2.8 at which Vp prime of t, the acceleration of the particle, equals 0. Well, if we're given one function and we want to justify why the derivative of that function has to equal a certain value, usually that involves using the mean value theorem. To use that theorem, we have to establish that we have differentiability and continuity over the interval. Specifically, we have to be continuous over the closed interval and differentiable over at least the open interval. So they told us here that Vp was a differentiable function. So that covers everything on this interval and anywhere else we might like to use the mean value theorem. But I do have to state in the beginning that Vp is differentiable and continuous on the closed interval from 0.3 to 2.8. This allows me to now use the mean value theorem. To actually use the mean value theorem, I have to find the average rate of change over this interval, and hopefully it's exactly 0, but let's give it a shot. So that's going to be Vp of 2.8 minus Vp of 0.3 over 2.8 minus 0.3. Now looking that up in the table, Vp of 8 is 55, or Vp of 2.8 I should say. Vp of 0.3 is 55 also, so we have 55 minus 55 over 2.8 minus 0.3. And this is a calculator problem, but you don't need a calculator to see that this is going to come out to 0 up top, which zeroes out the whole thing. Since my average rate of change is 0, the mean value theorem guarantees that V prime of c has to equal 0 for some c value on the interval from 0.3 to 2.8. IROC, there's going to be some IROC that equals this AROC somewhere on this interval. For this part of the problem, they want us to use a trapezoidal sum with 3 subintervals to approximate integral from 0 to 2.8 of Vp of t dt. All right, so I'm going to say that this stuff is approximately equal to the following. And if you don't write approximately equals, you're in trouble because we are not giving the true value of this integral. So let's see here. We've got 0 to 0.3. That's the first interval here. We have a base of 0 plus a base of 55 divided by 2 times a height of 0.3 to go from 0 to 0.3. So there we go. Next, for the next interval here from 0.3 to 1.7, we have 55 plus negative 29 over 2 times a base of, let's see, this is going to be 1.4. And then finally, this third trapezoid here, because they only wanted 3. You got to be careful and make sure you don't accidentally give them more than they asked for. We have a negative 29 plus 55 over 2 times a height of, let's see, 1.7 to 2.8. That's going to be a difference of 1.1. And at this point, you can, let's see, were there any units in this problem? Yes, there were. So this would have been meters, since you're taking the integral, basically, of velocity. That would have given you distance. So you can stick meters on the end and call it a day, or you can crunch the numbers on the calculator and see what it comes out to. So I went ahead and actually crunched the numbers on the calculator. Now keep in mind, again, you gain nothing from doing this, since your answer does not need to be simplified, but I did it anyway. So that's going to be 40.75, and again, that's going to be meters because we're taking the integral of velocity. For this part of the problem, we have a second particle, q, moving along the x-axis, so that its velocity over the interval 0 to 4 is given by this vq of t function, which is pretty insane looking. So we want to find the time interval during which the velocity of particle q is at least 60 meters per hour, and then find the distance traveled by the particle during that interval. All right, so first we got to plug this in our calculator and see what this looks like. Let's go ahead and do that. So here I am in my y equals in y1. I've got 45 times square root of x, and then we have the rest of this, and I'm using x instead of t because that's what my calculator likes for graphing things. Now, one thing you do have to be careful about entering this in is that the cosine should not be under the square root. Only the x should be under there. So just be careful with that piece of this. Now they want us to basically graph this on the interval from 0 to 4. So let's go ahead and change our window to go from 0 to 4. And then I'll do zoom 0, zoom fit. And let's see what this thing looks like. All right, so there it is. And actually, there is one more thing I have to graph. I need to figure out when this thing is at least 60 meters per hour. So let me go back to y equals. And in y2, I'm just going to enter the horizontal line 60. Let me zoom fit this again. And this will get both functions now so that I can see where they intersect. So there was VQ in all its glory. And here's the horizontal line 60. So if I want to know the interval at which this thing is at least 60, I have to figure out these two intersection points. And then I'm just going to give them the interval between these two intersection points, because everything between those results in the velocity being above that horizontal line. So let me do second trace, and then I'm going to do intersect, option 5. And then let me put my little spider there close to the first intersection. Press enter 1, 2, 3 times to get about 1.8662 and some change. And by the way, so I'm setting this equal to 60, showing people what I'm doing on my calculator. Here's what it looked like on the calculator. So at time 1.8662, I'm going to actually call that P, both on paper and in my calculator. I'm going to go in my calculator, quit out of that graph, and I'm going to store the answer I just got as alpha P. That way I can call it back quickly. Now let me go back to my graph there. There's my graph, and let me do second trace, option 5 again, and let me find that other intersection point now. My spider moves very slowly, but there he goes. Enter, 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 and that's about 3.5192. I'll write that on the paper here, and I'm going to call that point Q, which may be a little confusing because we have point Q, velocity of Q, but whatever. This is the constant Q. And then going back, into my calculator. There we are. Let's exit out of there. And let me do store. I'm going to store that as alpha Q now. So there it is. So let's see. Clearly, between P and Q, that's the interval that we want. So for the time interval, I'm just going to say VQ of t is greater than or equal to 60, is at least 60 on the interval from P to Q. And we've already defined what P and Q are, so that's what I'm going to put there. Now for the other piece of it, the distance we traveled on this interval, well, I mean, there's no direction change here, but just to be on the safe side, I'm going to call this distance the integral from P to Q of the absolute value of VQ of t dt, just to be on the safe side, because this guarantees I am actually getting the distance that the particle traveled. So let me go back now to my calculator, and I'm going to do the integral, so math 9, from p to q, so alpha p and then alpha q. And let me do absolute value. There we go. And I stored that under y1, so alpha trace y1 dx. And let's see what we come up with. It says 106.109. And this is the distance traveled in meters. So there we go. For this last piece on the problem, the final boss battle as it were, at time 0 they're telling us particle Q is at position -90. They want us to use the result from part B, and here's that result. That was just the approximation using a trapezoidal sum of this table up here from 0 to 2.8 of Vp of t dt. And they also want us to use the function Vq from part C. So here was that function again. And remember, we've actually entered this in our y equals, or at least I did, on my calculator. They want us to use all this to figure out the distance between particles P and Q at time 2.8. Okay, so we need to first get the positions of the particles. So the position of particle P is going to be the starting point, which they said was, let's see, particle P is at the origin at time 0. So that's going to be, this is xp of 2.8. That's going to be 0 plus this integral here from part B. So that's a total of, big surprise here, 40.75. And again, this is an approximation, so that's why I'm writing approximately equals. Now for xq of 2.8, that's going to be our starting position of -90, plus the integral from 0 to 2.8 of vq of t dt, which I will now have to solve on the calculator. So here's what that looks like on the calculator, and that comes out to roughly, dramatic pause here. Maybe I should just stop. Nope, there it is. 45.9377, I guess, if we go to 4 decimals there. And we just want to find approximate the distance between these particles. So we're just taking essentially the absolute value of the difference of these things. So let me just go back to my calculator, and I'm just going to take my answer there and subtract 40.75. So my approximated distance is about 5.188, and that is going to be meters.